Hey everyone. So in this video I like to review all of the ideas we've discussed when it comes to solving trigonometric equations. We've really covered a handful of different ideas and I'd just like to spend some time recapping this. And so when it comes to solving trigonometric equations, I like to think of trigonometric equations as falling in one of two different categories. And these names for these categories aren't really widely used, but I think it really helps us and describes what kind of techniques we will be using to solve the equation. And so one of the categories I'd like to call linear trigonometric equations. So these are trigonometric equations that only involve one trigonometric function raised to a single power. Right? So some examples might be the square root of 2 times sine of x plus 1 is equal to 0. Right, so here there's only one example of a trigonometric function. It doesn't have any powers, it's just raised to a single power. Another example might be tangent of x is equal to 5, or maybe even something like cosine of pi over 3 times theta is equal to -1. So these are all things that I like to call linear trigonometric functions. And then quadratic trigonometric functions, these are functions that involve multiple trigonometric functions, and maybe some of these trigonometric functions are raised to powers larger than 1. So maybe some examples can be 4 times cosine of theta sine of theta plus 3 cosine of theta is equal to 0. So that's one example. And maybe I'll just keep listing a few more. So let's say 3 sine squared of theta minus 7 sine of theta plus 2 is equal to 0. Secant of theta is equal to 2 times cosine of theta. And then maybe one more. Let's do 2 times tangent squared of x is equal to 3 times secant of x. And so the reason I call these examples on the right quadratic is because a lot of the techniques we use to solve these kinds of trigonometric equations require using the techniques we use in algebra to solve quadratic equations. So let's solve some of these equations just to review some of the ideas we've discussed. So let's begin by solving this trigonometric equation. The square root of 2 times sine of x plus 1 is equal to 0. So this is an example of a linear trigonometric equation. And whenever we're dealing with a linear trigonometric equation, we want to isolate that single trigonometric function in our equation. And so here we can do that by subtracting 1 away from both sides, giving us the square root of 2 times sine of x is equal to -1. And then to get rid of that coefficient of the square root of 2 besides sine of x, we can divide both sides by the square root of 2, giving us sine of x is equal to -1 over the square root of 2. And so now solving this equation is really requiring us to find the angle that sine takes to a y-coordinate of -1 over the square root of 2. And this might not seem so familiar at first, but if we multiply the numerator and denominator by the square root of 2 in this fraction here on the right, well, what we end up with is negative square root of 2 over 2. And this is one of our familiar side lengths to our special right triangles. Right, to our 45, 45, 90 triangle. And so if we draw out the unit circle, then what we really want to do is find the angles, all of the angles, that lead us to a y-coordinate of negative square root of 2 over 2. In other words, we want to find any angle that leads us to either of these points. And so here, if we're looking at 45, 45, 90 triangles that are below the x-axis, then really the angles we're looking for, at least two of them, are, well, here x is equal to 5 pi over 4. Right, 45 degrees past 180 degrees, and then also if we go 45 degrees shy of our full 360 degree rotation, we also end up with one of the valid angles, which is x is equal to, this would be 7 pi over 4. Of course, these are only two of the many angles that satisfy this equation. Any coterminal angle will lead to the same position and give us the same y coordinate. And so here, really what we're looking for is x is equal to 5 pi over 4 plus any multiple of 2 pi, any whole number multiple of 2 pi. So I'm going to write 2 pi n, where n is any number like 1, 2, 3, 4, or negative 1, 2, negative 3, negative 4, anything like this, where n is an integer. And then we get another family of solutions here, when x is coterminal with 7 pi over 4. So really the strategies we took for solving this trigonometric equation are, we wanted to isolate the trig function in our equation. And then the next thing we want to do is we want to find all of the solutions in one period of our trigonometric function. And so the last thing we want to do is we want to find all of the solutions in general, not just in one period. And so this requires including all of the coterminal angle solutions as well. So let's do another example of a linear trigonometric equation. We have tangent of x is equal to 5. And so before we really dig into things, let's make sense of what this equation is really asking us to do. Right, so tangent of x takes in an angle and gives us back a slope. So really what this equation is saying is that we want to find all the angles that lead to a slope of 5. And so here's a rough sketch of a line with a slope of 5. And so any angle that lands in either of these two positions is going to be a valid angle. Right, but 5 as a slope, as an output of our tangent function, it's not from one of our special right triangles. This is not an example of an angle we can just come up without any help. And so here, this is an example that requires the use of inverse trig. And so notice that if we take tangent inverse of 5, right, the inverse trig function, tangent inverse, is going to take in a slope, the outputs of our tangent function, and it's going to give us back the input of our tangent function, an angle specifically between negative pi over 2 and pi over 2. So this is going to be equal to one angle. There are many angles that do the job, but it's going to give us one of the angles. Negative pi over 2 and pi over 2, between negative pi over 2 and pi over 2. And so here, when we take tangent inverse of 5, we get roughly 1.37 radians. And usually you don't have to include radians as a unit, but I'm just writing it there to make it very, very clear. And so that's this angle here. This angle is 1.37 radians. And now how do we get the other example of an angle? Well, here we would just add pi to it, right? If we look to the other side of our unit circle, we'll end up with a part of the line that has the same slope. And so really here, x is equal to 1.37 plus, well, pi would give us another solution, or any other multiple of pi added onto 1.37 radians would give us more solutions, right? If I add pi again, we end up back at this original angle in the first quadrant, which had a slope of 5. And we could just keep doing this to get more examples of such angles. So here really it'd be 1.37 plus pi times n. These are the solutions to our equation, tangent of x is equal to 5. And so here, in this example, we had to use inverse trigonometric functions, but in cases where we encounter our values from our special right triangles, there I expect you to use exact values and be able to solve your equations without using inverse trig. So much like our previous example. So let's take a look at another example. Cosine of pi over 3 times theta is equal to -1. So in this example, what makes this problem a little bit trickier is that we have a coefficient of our input of pi over 3. And unfortunately, we can't do anything to get rid of this pi over 3. We can't divide it out, we can't factor it out. Really, that pi over 3 there in our input coefficient, it's really there to stay. But one thing we can do to sort of work with this a little bit is we can give this pi over 3 times theta a new name, right? If this pi over 3 times theta wasn't there, this would be a much more manageable equation. And so here, I'm going to just refer to this pi over 3 times theta. It's a number. I'm going to refer to it as u. So u is going to represent pi over 3 times theta. And so this equation becomes cosine of u is equal to -1, which is a much more manageable equation. We just have to know that we're not solving for u, we're really trying to solve for theta here. So when we get some solutions to this new equation, we have to sort of work backwards and make sense of what values of theta would truly work. And so let's try and solve this new equation now. And what we're really doing here is we're saying, well, cosine of u is going to be -1. What that means is that we're looking for angles u, which lead to an x value on the unit circle of -1, right? So here I'm looking at, here's all the points with an x value of -1. And so on our unit circle, an angle of pi, for example, would give us a cosine value of -1. And if we went all the way around our circle and then back, right, an angle of 2 pi, not 2 pi, 3 pi would also work, right? If we added 2 pi on top of pi, we'd end up at the same location, the same position on our unit circle. We get a cosine value of -1. Or if we went around again to 5 pi, this would also work, right? Odd multiples of pi would be valid inputs as u for this cosine function to give us a -1 out. And so here, really what we're saying is that u ought to equal, well, pi plus 2 pi n. These are valid angles for u to make our equation true. But again, we're not looking for values of u, we're looking for values of theta that make this equation true. And we just have to remember now that u is the same as pi over 3 times theta. And so if I want to get theta by itself now, and really get the solutions to our original equation, well then I would undo that multiplication by pi over 3, I would divide by pi over 3, or in other words, multiply by 3 over pi. And so let's do that. Let's multiply by 3 over pi to both sides of the equation. And so this would require distributing 3 over pi to both terms on the right-hand side. And so on the left side, we end up with theta. And on the right-hand side, well, pi times 3 divided by pi, that's just going to be 3. And then 2 pi n divided by pi, well, that's going to give us 2 pi, or 2n, and that's still multiplied with 3. So this gives us 6n. Where n, these are just whole numbers, right? 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, and 0. Right, so maybe I'll just list out some solutions here, right? So we're saying that values of theta that are solutions to our original equation, well, they're 3 plus 1 multiple of 6, 2 multiples of 6. Here we've got 15, 21, 27, and so on. But also things like -3, maybe I'll go one more further, -9, these would also be valid. So that's a list of numbers that we're really getting as the solutions to our equation. And so maybe let's test one value just to really convince ourselves. Maybe let's look at this value of 15. Theta is equal to 15. Let's check that this is truly a solution to our original equation. Cosine of pi over 3 times theta is equal to -1. And so here, if we check, we've got cosine of pi over 3, and we're saying, one example of a solution is when theta is equal to 15. So I'm going to let theta be 15. And I'm asking, is this equal to -1. Well, here cosine of pi over 3 times 15, that's cosine of 5 pi, right? 15 divided by 3 is 5, so we've got cosine of 5 pi. And we saw earlier that this does equal 1, right? Here, if we look at our unit circle, if we go around pi, and then 2 pi more, that'll be 3 pi, and then 2 pi on top of that, that'll be 5 pi, and that'll still bring us to this leftmost point on our unit circle, giving us an x-coordinate of -1. And so cosine of 5 pi will give us -1, telling us that 15 was a valid input, a valid solution to this original equation. And so really when it comes to solving these linear trigonometric equations, the steps we want to take more or less are, well, first we want to isolate the trig function, right? There's only going to be one. That's the idea of what a linear trigonometric function is. We want to isolate that trigonometric function. And then if there's a coefficient to that input, we want to substitute out that input to our trigonometric function, make it less complicated just for a moment to find solutions to a much more simple equation. So substitute away the input if necessary. Right, so the substitution we made in the last example was we replaced that input with the variable u just for a moment. This is what I mean by substitute. And then in this new equation, we're going to find the solutions in one period. And so usually there will be two solutions, sometimes there will just be one. And then when we have those solutions in one period, we want to extend these solutions to all the solutions. Right? So we want to include the coterminal angle solutions. And then lastly, we want to reverse the substitution if we substituted earlier. Right, so in the last example, we substituted u was equal to pi over 3 times theta, and then we solved that new equation, but we got answers in terms of u, which is not what we really wanted. We wanted answers in terms of theta, and so we have to sort of reverse that substitution. And I guess one last thing I should say is that here, when we want to find the solutions in one period, it might be the case that we need to use inverse trig. Right, so here, use inverse trig, but only if necessary. Right, if we can get away without using it, that's ideal. So what about solving quadratic trigonometric equations? Well, here, let me write these steps out on the right. So there's not much really to say about this. One thing that can make quadratic trigonometric equations a little bit more challenging is that sometimes they'll involve multiple kinds of trigonometric functions, and this makes things a little bit less clear. And so one step we can do sometimes is use identities to rewrite our equation in terms of just one kind of trigonometric function. So here, one step I might recommend is use trig identities to rewrite the equation in terms of one trig function. And then maybe from there you can use the techniques we've learned in algebra for solving quadratic equations to solve this quadratic trigonometric equation. Right, so here typically the approach we'll take is we can solve by factoring. Might also be the case that you can solve using the quadratic formula or using square roots, but I think typically for the examples I'll give you, factoring might be sufficient. So let's solve this trigonometric equation. Secant of theta is equal to 2 times cosine of theta. And so one thing I notice right away is that secant of theta, that's the reciprocal trigonometric function to cosine of theta. And so we can clear things up by multiplying both sides of our equation by cosine of theta, giving us 1 is equal to 2 times cosine squared of theta. And now this is a quadratic trigonometric equation, we can really see that second degree, that second power of this cosine function here. And so one thing I can do from our algebra techniques is I can take the square root of both sides, plus or minus the square root of both sides. But first let me get that square part alone. So if I divide both sides by 2, we get 1/2 is equal to cosine squared of theta. And then taking plus or minus the square root of both sides, this gives us cosine of theta is equal to plus or minus the square root of 1/2. And now we're just dealing with linear trigonometric equations. So one thing we can do to make this a little bit clearer is notice here that this is the same, plus or minus the square root of 1/2. That's the same as plus or minus the square root of 1 over the square root of 2, which is 1 over the square root of 2. And we saw in one of our first examples that this is the same as the square root of 2 over 2. And so solving this equation really amounts to looking at our unit circle and determining what angles theta give us an x-coordinate of plus the square root of 2 over 2 or minus the square root of 2 over 2. Now really these all correspond to 45-degree angles away from our x-axis, or horizontal axis. And so really we can see that this is pi over 4. If we're just looking between 0 and 2 pi, this is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And all their coterminal angles. And so one way we can express this is, well, first off, notice that really this is 90 degrees added on to pi over 4. This is 90 degrees added on to pi over 4. These are all just 90 degrees away from one another. I can write this as pi over 4 plus pi over 2, 90 degrees times n, right? Any multiple of 90 degrees added on to pi over 4 will give us another solution to our equation. Now let's take a look at one last example. We have 2 times tangent squared of x is equal to 3 times secant of x. And again, we're dealing with an equation involving multiple kinds of trigonometric functions. And so here we can use an identity to try and remedy this. And the most frequent identity that we'll use when it comes to trying to solve these trigonometric equations is the Pythagorean identity. And here we're not dealing with sine and cosine, but maybe let's start there. Right, so remember that the Pythagorean theorem for our trigonometric functions, sine and cosine, looks like sine squared of x plus cosine squared of x is equal to 1, right? As long as they're the same angle, the square of sine of that angle plus the square of cosine of that angle, that's always going to equal 1. When we divide both sides by cosine squared of x, we'll get sine squared of x over cosine squared of x, cosine squared of x over cosine squared of x, and 1 over cosine squared of x. This gives us tangent squared of x plus 1 is equal to secant squared of x. So here we've got a new Pythagorean identity relating tangent and secant. And this is a way we can convert powers of tangent into powers of secant. Namely, if I subtract 1 away from both sides on this equation here, I've got tangent squared of x is equal to secant squared of x minus 1. And so if we look back to our original equation, we can replace that tangent squared of x using our identity, right? 2 times tangent squared of x. Well, tangent squared of x is equivalent to secant squared of x minus 1. And this is equal to 3 times secant of x. We want to solve this new equation now. And so let's distribute this 2, giving us 2 times secant squared of x minus 2 is equal to 3 times secant of x. And then subtracting 3 secant of x from both sides gives us 2 times secant squared of x minus 3 times secant of x minus 2 is equal to 0. Now this is where we want to use our quadratic formula, quadratic equation techniques. Here we've got a quadratic equation in terms of secant of x. Right here we've got secant squared of x, we've got secant of x. We can factor this. And here I notice that if I'm going to get 2 times secant squared of x as my leading term, then this is going to require multiplying 2 times secant of x with secant of x. Next, if I'm going to get this minus 2 at the end of the day, and this minus 3 secant of x, well, I know I'm going to need this minus 2 and plus 1 somewhere, or minus 1 and plus 2. But here, because I've got 3 secant of x that I'm subtracting away, I'm going to expect more, a larger negative number. So here, I'm going to fit negative 2 here and positive 1 here. Right? This way, we see that we've got negative 4 sets of secant of x and plus 1 set of secant of x when we multiply this out, giving us that negative 3 secant of x. And so now when we try and solve by factoring, right, one side's 0, the other side is factored, what we do is we ask, when are these individual factors 0? Because when they're 0, they'll multiply and make the entire quantity on the left side 0 and make the equation true. So really what we're asking here is to solve the new equations, 2 times secant of x plus 1 is equal to 0, and secant of x minus 2 is equal to 0. So let's solve this equation now. So here, let's start with the left example. So on the left, when we get that trigonometric function alone, we've got 2 times secant of x is equal to negative 1. We've got secant of x is equal to negative 1/2. And then we can rewrite this as 1 over cosine of x is equal to negative 1/2. Now here, I'm not a big fan of this cosine of x in the denominator. Let's sort of shuffle things around. Let's multiply both sides of the equation by cosine of x, giving us 1 is equal to negative 1/2 cosine of x. And then let's multiply both sides by negative 2. Right, so this gives us negative 2 is equal to cosine of x. And so now this is asking us what values, what angles, when we input to our cosine function, give us negative 2 as an x-coordinate on our unit circle. Well, if we draw our unit circle out, and we look at negative 2 as an x-coordinate on our unit circle, well, no value of theta is going to give us this x-coordinate on our unit circle, right? This has a radius of 1. So this is negative 1 out here. We never reach an x value of negative 2. Here there are no solutions contributed from this factor. But there may be solutions from our other factor. We have to check. So let's look back up. Now we've got secant of x minus 2 is equal to 0. And we can go through the same motions, right? Secant of x is equal to 2, adding 2 to both sides. We can rewrite this as 1 over cosine of x is equal to 2. And multiplying both sides by cosine gives us 1 is equal to 2 cosine of x. Dividing both sides by 2 gives us 1/2 is equal to cosine of x. And now here, this is a much more familiar kind of trigonometric equation. We're looking at all the values, all the angles, which give us an x-coordinate on our unit circle of 1/2. Well, here that happens at pi over 3. And what is this? This is 5 pi over 3. At least these are the solutions in the period, or 0 to 2 pi. But, we're looking for all of the solutions, so here we really want to state all the coterminal values as well. X is equal to pi over 3 plus its, coterminal angle, so plus 2 pi n to get the other coterminal angles. And x is equal to 5 pi over 3 plus 2 pi n to get the coterminal angles with the position, the bottom half of our unit circle, that lead to a cosine value of 1/2.